We're back after the coffee break, and it's my pleasure now to introduce Sami Okazaki. And Sami has recently joined Manchester in a joint position with Aalto University in Manchester, and is going to form new alliances between Aalto and Manchester, and between Manchester and the rest of the EU, I think, because Sami is one of the leaders of AI in EU and has been heavily involved in the ELIS machine learning lab across Europe, which was recently funded for the ELISE project, which Sami led on. We hope to get more and more involved in that in Manchester, and hope to keep UK working in Europe despite political shenanigans. Sami's going to talk about data analysis with humans, and over to you, Sami.
Yeah, thanks, Magnus. Thanks for the kind words. Let's see if I can do the sharing. Seems to work. So do you see my presentation slide or the other slide? I can't see which one you are seeing.
It works, yeah.
Okay, very good. Okay, yeah, thanks. So, and thanks for all the organizers for the invite. So data analysis with humans. I'll come to why the title is like that in a second. So the starting point of the talk, if I can, yeah, works. Starting point of the talk is generative probabilistic modeling, where we have some observations of the world, the data set, and our task is to build a model of the world that has some parameters. And we would assume a stochastic model that induces a distribution in the data space. And now, as you notice, there is no users in this picture, right? So what does that imply? That we normally don't have users in our models, even though, of course, there are humans using whatever comes out of this. Is either because the users don't exist, are not relevant for this analysis. We just set up the model and then let the systems run as they run. Or then we consider that the users are part of the world from which the data comes. But in that case, this goes a bit against the nice idea of probabilistic generative modeling, that we would actually we would formulate and explicate our assumptions of the world as part of the model, and then when we do the learning, the model remains interpretable in a nice way. So if we don't have the users here, then we will be missing that aspect. Further, for the motivation, and yeah, the keyboard really doesn't work today. It has worked always. I'll have to try to use the mouse. Okay. For the purpose of this talk, I'm dividing the data analysis world into two different types of problems. On the left, we can see most of machine learning, most of data mining, where the user is needed very little when the system is in operation. And the AutoML, automating machine learning, taking the human completely in the loop, is an extreme example of that. But that's not the all problems that there are in the world. There is also visual analytics, where the goal is through advanced visualizations, interaction, to get the user to understand better what the data is telling. And maybe the extreme example is information retrieval, which would be completely impossible without the user, because there's a single user who has all the knowledge about what is relevant, and nobody else can actually help in the information retrieval task. The point I'm trying to make with this slide is that in the middle, there is a big gray region of problems which are being studied relatively little compared to how important they are. And that's one of the reasons why I'm particularly interested in this one and many others at the moment. So since the system will ultimately see the user as data at some point, it makes sense to start by assuming the user as a data source, considering what can we do if the user is a data source. So then, in addition to the model of the world, we would have a model of the user, we would have observations both of the rest of the world and the user, and we would be fitting models. So a simple example is the standard supervised machine learning setup, or regression or classification setup, where we have a learning data set with some predictors X and known outputs in the learning data set Y, and our task is to learn a function that maps X to Y, so that for new data where we only have X, we will be able to do predictions of Y. So we all, of course, know about this. So in precision medicine, what the X would be molecular or clinical measurements of a patient. So one observation is a patient, and then the prediction would be which treatments would work for this particular patient. Why this is difficult is that the learning dataset is too small to do this just statistically by estimating these predictors from the data, and we need to collect more data, and the users are, of course, then one source of that data. The users come with one catch, that we typically would not want to waste too much of valuable experts' time, so we would want to ask minimal number of questions to get maximal improvement in the predictions in this case. So what we did in this case is we asked the experts about the relevance of a particular feature, which was now a genomic or clinical variable for effectiveness prediction of one drug, one treatment. And this is a really difficult question for the experts to answer. So most of the time they had to answer, I don't know, but sometimes they were able to answer relevant or irrelevant. And then we improve the prediction model and then decide again what to ask. So we need a model for this. And I presented the model separately, the user and world model. World in this case is a patient model, and the user is the expert. But we need to tie them somehow together if we want to improve the predictions by asking the expert. So what we did here, we assumed that there is an unknown relevance for each variable, which we need to infer from the data. And when we ask users, they answer about the same relevance, but they may make an error. So because the individual users may know different amounts of different drugs. And also the error probability for the users is unknown, and we need to estimate that from the data. And how do we do the estimation is through sequential experimental design, which is a variant of active learning, or also called Bayesian automatic experimental design, to maximize the expected utility, which is to minimize the prediction errors. So we did this for real data, real users, but I'm showing real data simulated users. Here the task was to predict cholesterol levels in blood of individuals based on measurements, genomic measurements. And the simulated expert was constructed by having the simulated experts see a bigger cohort of people, different cohort, and then it answered according to what it had observed in the bigger data set. So how does this work? How well does this work? As a function of how many questions we asked, the error, mean squared error, does not decrease at all, actually, if we ask in a random order up to some 1,000 questions. Whereas if we ask with the method that I briefly described, we get an improvement. And if we do the personalized medicine questions, so we target the questions to improve maximally an individual patient and then average over the patients, we get an improvement of about 70% of the available improvement in 1% of all possible queries, 80% in 250, which is 2%, which is a radical improvement in the number of questions we would need to ask if we just asked in the random order, but still 250 questions is a lot. On the other hand, if this is a matter of life and death, as it here is, then I mean, okay, maybe not the cholesterol levels, but in more serious cases, then the expert might want to be bothered. Another example is from material science, where the problem to be solved is how does this molecule that you see here bind to the surface. This could be solved in principle by an intensive array of molecular simulations, materials science simulations, but that would require so many simulations that we would rather avoid the intensive carbon footprint. And we asked the experts about good starting points or regions of the space where to do the modeling. And how we do this is we provide the expert a slider that you see here. So the expert can now move the slider, and their task is to set it in a position where this molecule is most likely to bind. Then the AI designs the next slider, and with the minimal number of sliders, we should find the starting point. So in principle, this problem could be solved with Bayesian optimization. So asking the expert for the energy value for a particular configuration, but the expert wouldn't be able to answer this. So what the experts could answer or would be able to answer is that how is it more likely that this the molecule would bind in this configuration than in that other configuration? But the problem with this is that we would need to ask a lot of questions in order to find good configuration. So what we are doing is we are asking the maximum for the maximum on 1D subspace, and then we choose the next subspace until this converges. So this work is coming out in ICML in a couple of weeks. So up to now, I've assumed the user to be a passive data source, which is good for prior elicitation, interactive prior elicitation, minimizing the number of questions or asking on a budget. But at least I don't consider myself a passive provider of data to my computer. I actually am thinking that I am controlling the computer to do what I want. This may, of course, not be true, but anyway, I believe many of you guys also are thinking in the same way. So does this actually matter that we are active in that sense? So we designed a simple game to study this. So the AI's task here is to find the maximum of a function f that you see on the left. But the catch here is that the AI doesn't see this function. Only the user sees the function, and the AI can ask individual points of the function. So AI can ask the user for points of x, and now the goal is to ask minimal number of questions. So the AI has its own representation, kind of a mental state or a surrogate model, which in this case is this dotted blue line here, which comes with uncertainty shown by these shadings. It's a Gaussian process for those who are interested in that kind of stuff. Now the AI has seen two observations, and it is asking me as a user to give the value at this location. So if I answer truthfully, what the AI will most likely do is, because it probably assumes the function to be continuous, it thinks that the optimum cannot be very close to this point, right? That's why it wouldn't probably ask here next, while even though that's the best place, it would ask here or here. So that's why I might want to consider answering here. I mean, I do have the degree of freedom to actually lie to the AI. So if I answer here, then the AI might think that these values are quite possible, and it might converge quicker. So what I said was speculation. We did a user study, and the users actually are able to improve the AIs. Users are able to help the AI reach the optimum quicker than with standard Bayesian optimization, which is already really good. And how they do this is by giving incorrect values of the function. So the users are able to steer in this way. So what I would be concluding from this is that even in these kinds of very simple cases, instead of assuming that users are passive, we need to assume that they are active, and then we need to ask, where do we get the models from, the user models from? And my answer would be that in the standard way, how would we otherwise do modeling? We need to either have prior knowledge, or then we need to have data from which we learn, or preferably both. So cognitive knowledge. There are cognitive models. They are typically of the simulator type, so that we don't have the likelihoods in an explicit form. We can only simulate data, and still we would need to do the inverse modeling to infer the parameters of the user models. I have so limited time that I'm not going into details on this, just pointing out that we have done this for some certain kinds of cognitive models. And for those who are interested in this general framework on how to do inference on simulated types models where we don't have the likelihoods, we have set up a community resource engine for likelihood-free inference. If somebody is interested in contributing to this, it's an open source package. You are all very welcome. But now the users are even more complicated than, of course, at least we'd like to think that we are more complicated than what I led on so far. So we actually have a representation of the AI we are interacting with. So we need to go beyond the standard mindset of machine learning, which is that the users are passive, or human-computer interaction where the AI is passive. So both are intelligent creatures, at least at some stage. And in particular, if we want to have AI assistants that would actually understand what we aim at, instead of just taking us as literally, which is very frustrating. For that, we need to have an AI assistant that understands that we are goal-oriented and can infer our goals. And further, they need to have an understanding that we are thinking of why is the AI suggesting to me what they are, right? That is what I meant by the model of the AI. If we have these kinds of models, then we can improve in information retrieval, for instance, we can improve on the performance of just having a naive model. How did we do that? Is we considered the user as a teacher. So the user is trying to teach the AI what the user wants to do. And the AI has a model of its teacher, which is the user, which also has a model of the AI, with which it interprets how the AI's responses or suggestions. So 3 levels of user models. I will be very brief on 2 more things, just mentioning them. So most often it's the user who has the final call on whether the decisions are taken out, and the AI can just make recommendations. For this, the AI can help much better if it has a model of how does the user make the decisions. We can, of course, build such models, take them into account, improve performance. We had a paper on this in last year's ICML. And then one more thing I'd like to point out is what types of applications do we think that these kinds of considerations that I presented would make the biggest difference? So this is one very broadly applicable scenario, which we call AI-assisted design. So the design task here can be engineering design, it can be experimental design, or it could even be fashion design, I don't know. Anyway, it's a collaborative design setup where the goal is implicit. So the user is in charge, and when the user sees a good design, the user will recognize it as a good design. AI can recommend, and now it can recommend better if it can anticipate what would be useful for the user, and for that it needs to have a model of the user and what the user is doing in this system. And that would be the type of model that I was hinting at. So to summarize what I presented, I first talked about passive user models, which are good for generalizing prior elicitation, knowledge elicitation. Then I talked about user models with increasing levels of sophistication, first active user models, assuming that the user has an agenda, and then further user understanding that the user understands that the AI has an agenda. And I was arguing that that might be already a sufficient level for having AIs that are actually helpful. For that, we need to include cognitive knowledge, where we can apply approximate Bayesian computation or likelihood-free inference. Then I pointed out that the user often ultimately decides, and for that it would make sense that the AI would have a decision-making model of the user with which it can also make itself more understandable. And then I pointed out that these kinds of tools and techniques are probably needed the most in cases where the user knows the goal, but only implicitly, so the user needs AI's help, and AI-assisted design was one of these kinds of scenarios. All the papers code is available under these links, and just leaving the collaborators' names here. So I certainly didn't do all this work alone. Thanks a lot for your attention.
Thanks, Sami. Very interesting talk. Let me just check. Okay, so I don't see any questions in the Google Doc. If anyone wants to ask a question, they can just ask one in the old-fashioned way by switching on the microphone and talking. But I think I have a question while people think. So machine learning has been really successful in the kind of high volume data scenario, and we've kind of gone down to looking at pixels rather than features, and really kind of you know, an image processing, or we've gone down to very low level kind of highly dense high information content data where the big successes in machine learning have been arguably recently, or the sort of headline grabbing ones. But now you're talking about modeling users, and that reminds me a bit more of kind of low information density problems like non-verbal communication, or kind of hints, or things that we maybe associate more with human intelligence than maybe what we associate with deep learning and fields like that. So do you think the kind of models that we need to understand users may be different from the ones that have been very successful in machine learning recently?
Right. Yeah. I very much agree with what you are saying. So maybe, okay, I think we need two kinds of models. So for some applications, we would have lots of user model data available, or data available of users to learn the user models. Like recommendation engines obviously would be these types of things. But then there are things that can only be inferred online during the interaction. Like what are the specific things that I have in mind now that we are talking, right? And of course, you already have constructed the model in your mind on this, and that's the only way how we can communicate through a very narrow bandwidth channel in Zoom at the moment. So for that kind of thing, there needs to be more. It needs to be more data efficient. But probably to be maximally useful, the AIs will need to have models of the kind of outside world, and where there may be, of course, high intensity data. But also for the interaction, it needs to have these kinds of different types of low information content models.
Well, I mean, recommender systems is a really good example where machine learning solved a problem in a way that's completely different from how humans work out whether they're going to enjoy films or not, you know, or so, but now I think you're sort of saying maybe there's more information also to be learned from people using, you know, people maybe using recommender systems. Maybe the way they use them has some implicit information that we're missing by just looking at their choices somehow. If you can elicit that information.
Yeah, I think some people in the recommendation engine field are going a bit to this direction, asking that could the engines be better if they would try to understand the users right now, which is of course a much more difficult task. Or at least that's what we think at the moment. You never know beforehand.
Yeah. Let me see if there's any questions that appeared. Here's some questions. Okay. Okay, there's a question from Elko Bakker. I've heard some people pushing multi-agent games like Hanabi as a good test space for AI agents interacting with each other. Do you think that would be useful for your work in AIs interacting with active users? It's related to AIs actually interacting with each other.
Yeah, definitely. Yes and no. So the multi-agent learning typically is focusing on slightly different angles of this problem. So the difficult problems are different if they are all agents, non-human agents, than with humans. But the formalisms can be very similar. And definitely I'm expecting to see that some kinds of games which would be simulating interhuman interaction too, and asking questions like, can we generalize? Can we have self-play that would actually help in playing against humans, or in collaborative settings, which I'm normally studying, would actually make the agents more helpful for humans?
Great.
Good question.
Okay, so we're going to wrap up.